Enzymes are globular proteins with a specific tertiary structure, held together by ionic and hydrogen bonds. The shape of the tertiary structure determines the shape of the active site, and a substrate will be complementary to the particular shape of the active site. Enzymes work by catalyzing a reaction, reducing the amount of activation energy needed for the reaction to proceed. There are two theories for how substrates fit into enzymes: lock and key theory and induced fit theory. In lock and key theory, the substrate fits into the active site where it is held in place so the reaction can go ahead. With induced fit theory, as the substrate molecule collides with an enzyme's active site, the enzyme molecule changes shape slightly, making the active site fit more closely around the substrate. This reshaping breaks some of the bonds in the substrate, reducing activation energy to catalyze the reaction. As shown by the graph, an increase in heat causes an increase in enzyme activity and so rate of reaction. This is because enzymes and substrates have more kinetic energy. They vibrate and move around more, increasing the chance of successful collisions. Successful collisions mean more enzyme-substrate complexes are formed, and therefore there is a higher reaction rate. However, this only occurs up to an optimum temperature. After an optimum temperature, the temperature becomes too high to aid enzyme activity. As there is a further increase in kinetic energy, there is more vigorous vibration capable of breaking hydrogen and ionic bonds with holding the enzyme in its tertiary structure. A tertiary structure change leads to the change of the active site, an irreversible change called denaturation. Effects of concentration. By increasing the concentration of enzymes, the initial rate of reaction increases and more active sites become available for enzyme-substrate complexes to form. However, it only occurs up to a certain point. After the optimum concentration of enzymes, substrate molecules are all used up and decrease in number. The frequency of collisions decreases and therefore substrate concentration becomes a limiting factor. We can see a similar scenario when we increase the substrate concentration. As with increasing enzyme concentration, the initial rate of reaction increases as more substrate are available for successful collisions, and therefore more enzyme-substrate complexes form. However, the reaction reaches a point at which all the enzymes present are working at their maximum rate, and so further increase in substrate concentration will have no effect. Enzymes become the limiting factor. By altering pH, we can also affect the enzyme activity. pH is the measure of hydrogen plus ions. The higher the concentration, the lower the pH value. Therefore, acids contain a high concentration of hydrogen plus ions. As shown by the graph, a change in the hydrogen ion concentration can interfere with the enzyme activity. This is because charges of hydrogen and ionic bonds are altered, and therefore the enzyme loses its tertiary structure. If the shape of the tertiary structure changes, then the substrate shape will no longer be complementary to the active site. The enzyme-substrate complexes will not be able to form, and therefore enzyme activity will significantly decrease. Different enzymes work at different optimum pHs. Usually this is around pH 7. However, an enzyme present in stomach acid, which obviously has a high concentration of H plus ions, works at an optimum pH of 2. Enzyme inhibitors work by reducing the rate of reaction of an enzyme. They do this in two ways, depending on their type. There are two types of enzyme inhibitor: non-competitive inhibitors and competitive inhibitors. Non-competitive enzyme inhibitors work to reduce the enzyme activity by binding away from the active site at an allosteric site. By doing this, they irreversibly change the shape of the enzyme's active site so that the shape of the substrate is no longer complementary. The substrate cannot bind to form enzyme-substrate complexes, and therefore the reaction cannot be catalyzed. This cannot be altered or changed, and so therefore by increasing substrate concentration there will be no effect on the enzyme activity as shown in the graph. In contrast, the effects of competitive inhibitors can be reduced. Competitive inhibitors work by forming a similar shape to the substrate. They bind to the active site of the enzyme in place of the substrate. Therefore, the substrate cannot bind to the enzyme to form an enzyme-substrate complex, and rate of reaction decreases. As previously mentioned, the effects of competitive inhibitors can be reduced by increasing substrate concentration, as shown in the graph, where the red line represents competitive inhibitors. As substrate concentration increases, so does the rate of reaction. This is because there is a high abundance of substrates to be able to compete more successfully to form enzyme-substrate complexes. As the substrate concentration increases, the rate of reaction with the competitive inhibitor, shown by the red line, reaches the rate of reaction with no inhibitor, shown by the blue line.